Welcome all to Maths the Number Game. In today's maths session, we shall be discussing about a new set of numbers known as squares. We shall study interesting patterns and properties of these square numbers. So let's begin. Before we start the session, a small note to the students. Maintain a single line notebook for writing the notes and to solve the exercises. The text highlighted in blue color should be written in your notebook as per the explanation notes attached to this video. The exercises and practice sums must also be done in order in your notebook as per the given textbook. So let's begin session 1, that is exercise 6.1 of squares and square roots. In this session, we shall be studying the following as per the NCERT textbook page number 96, exercise 6.1, namely Introduction to Squares and Square Roots, Properties of Square Numbers, and Interesting Patterns of Square Numbers. Introduction. What is a square? What comes to your mind when you think of a square?
A four-sided polygon.
Right. You think of a four-sided polygon with all the sides
Equal.
Yes, you're right again. When you look at the square, you see that all the sides are equal. Let us take for example this particular square 2 by 2. That is, the sides are 2 by 2 or the area is 2 by 2, that is 2 square, or it is equal to 4. If you split the square into 4 equal parts, each square is a unit square. So it is made up of 4 unit squares, or in other words, 4 is called the square number. Let us take another example. One side of the square is 5 and the other is again 5. So this is a square of side 5 by 5, or its area is 5 square, and when you multiply you get 25 squares. When you look at this figure, you find 25 squares. So 25 again is a square number. 2 is called the square root of 4, and here 5 is called the square root of 25. Now let's go further and find the table of squares, a very interesting table. Let's start from 1. 1 into 1 is 1 square, so it is equal to 1. 2 into 2 is 2 square, is equal to 4. 3 into 3 is 3 square, that is 9. 4 into 4 is 4 square, that's 16, and so on. 1, 4, 9, 16, 25, 36 are all called square numbers. I would prefer that you study this table of squares at least up to 20 square. It is a very useful table, just like your multiplication tables. Next, let us find what are the properties, what are the patterns based on this table. Can you see a pattern of the unit digits? They all end with 1, 4, 9, 6 and 5. They do not end with 2, 3, 7, 8, or either do they have an odd set of zeros. So what can we conclude? We can conclude that numbers which end with 2, 3, 7, 8 or having an odd number of zeros are never perfect squares. And the second conclusion we can come to is all square numbers will end or must end with 1, 4, 5, 6, 9 or even number of zeros. But all numbers ending with these digits need not be square numbers. For example, 21 ends with 1, but it is not a square number. 54 again ends with 4, but again it is not a square number, and similar examples are given. Another conclusion we can make is that every even number has an even square and every odd number has an odd square. Now with these properties, let us try to solve exercise 6.1. The first three questions is 1, 2 and 3. What will be the unit digit of the squares of the following numbers? So, example 1 is 81. Now, to find out the unit digit, we normally have to multiply 81 into 81. That is 1 into 1 is 1, 1 into 8 is 8, 8 into 1 is 8 again. Here 8 8s are 64 and we get a total of 6561 and the unit digit is 1. Do we have to go through such a long process? No, not at all. Maths is a very simple game. So let's find out the trick in this game. All you have to do is to multiply the units place of the square or find the square of the units place. I shall explain. Here the units place of 81 is 1. You have to square 1. That is 1 into 1 is 1. So the answer to this question is 1. Let us take another example. 272. What is the units place? 2. So what is the square of 2? It is 4. So the answer will be 4. Similarly, coming to the third sum, what is the units place? 9. And what is the square of 9? It is 81. So again, the units place there is 1. So the answer is 1. Similarly, for the next sum, 3853, 3 is in the units place, hence the square of 3 is 9. So the unit digit of the square will be 9. I hope the sums are clear. I would like you to work out the sums from 5 to 6 on the same principle. The second question. Following numbers are obviously not perfect squares. Give reasons. 1057. Now let's recall a property we just learned previously. We remember that the numbers which end with 2, 3, 7, 8 and odd number of zeros are never perfect squares. Applying the same rule, we can solve all these problems very easily. 1057 ends with 7, 23,453 ends with 3, 7,928 ends with 8 and 2,22,222 ends with 2. So all these numbers end with the digits 7, 3, 8 and 2 respectively. Hence they are not perfect squares. The squares of which of the following would be odd numbers? Again, this is the property which we learned in the beginning. We know that any odd number has an odd square and even number has an even square. So for example, 431 ends with is an odd number, hence its square is obviously odd. If it ends with an even number, the square is also even. So it is not odd. So the answer here, the question asked is the square of which of the following would be odd numbers. So the square of 431 is an odd number. For additional practice, try these on page number 90, 91 and 92. Now coming to some interesting patterns of square numbers. Have you heard of triangular numbers? Let me explain. Numbers whose dot patterns can be arranged as triangles are called triangular numbers. How do we arrange them? For example, put 3 dots here. In the next row, put 1 less, that is 2 dots and 1 dot. So you get a triangular figure. Count the number of dots. 1, 2, 3, 4, 5, 6. So 6 is a triangular number. Similarly, let us draw another pattern with 4 dots, starting from 4 dots up to 1 dot in decreasing order. You get another triangle. Count the number of dots. You have 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So 10 is again a triangular number. Let us add them up. 6 plus 10. What do you get? 16. And what is the surprise? When you join this pattern, you get a square and the number of dots in the square is 16. So 16 is nothing but a square number. So when you add triangular numbers, you definitely get a square number. Try to find more triangular consecutive numbers. Another pattern. Observe this pattern here. 1 square is equal to 1, 11 square is equal to 1, 2, 1, 111 square is equal to 1, 2, 3, 2, 1 and so on. You see that the middle number is 3 and it is reducing on either side 2, 1, 3, 2, 1. Again here in the next, when it's 4 digits, you have 4 in the middle and it reduces from 3 to 1. And again here 3 to 1. Now repeat here, you have 5 ones. So here it starts with the middle number 5 and reduces on either side. And can you try and find the answer for the last one? Another interesting pattern. 7 square is equal to 49. 67 square is equal to 4489. As you develop this pattern, you see that as the number of 6's increase, there are number of 4's, 8 and 9 increase in a particular order. Try and find the missing number. Very interesting, isn't it? Coming to the next set of questions of exercise 6.1 is again a pattern which you have to develop by looking at the numbers. Again here you have 11 square is 121 and 101 square you have a 0 on either side of 2. And for third pattern you have 2 double 0. Again there is a double 0 on either side of 2. If it is 4 zeros, there are 4 zeros on either side of 2 and so on. Now coming to the sixth question, again this is another pattern of square numbers. The explanation is given below. They say 1 square plus 2 square plus 2 square is 3 square. You don't have to find the squares of the numbers, you just have to observe the pattern. Observe the pattern of the first 3 rows. The first base number into the second base number, that is 1 into 2, is equal to 2. Yes, and the next consecutive number is 3 and 3 square is the RHS. Similarly, 2 into 3 is equal to 6 and its next consecutive number 7 is in the RHS and 7 square becomes the RHS. Similarly, 3 fours are 12 and 13 is again in the RHS. All are squares. When you actually multiply them, you find that the values are correct. For a detailed method, you can read the explanation given below. You can apply the same pattern for another sum, that is 10 square plus 11 square plus 110 square is equal to 111. Try it out and let me know the result. Let us learn some more interesting properties of square numbers. Adding odd numbers. Let us add odd numbers starting from 1. 1 plus 3 equals 4. 1 plus 3 plus 5 equals 9. 1 plus 3 plus 5 plus 7 equals 16. 1 plus 3 plus 5 plus 7 plus 9 equals 25. You note that all the answers are all perfect squares and the numbers added are all odd numbers starting from 1. So we can conclude that the sum of the first n odd numbers is a square number. Let us observe 1 plus 3. There are 2 odd numbers, so 2 square is 4. 1, 3, 5. There are 3 odd numbers, so it is 9. And here 1, 3, 5, 7. There are 4 odd numbers, so it is 4 square, that is 16. And in the last row you have 5 odd numbers, so you have 5 square, that is 5 into 5, that is 25. So let us solve the problems based on this property. Without adding, find the sum of 1 plus 3 plus 5 plus 7 plus 9. You simply don't have to add. Instead, count the number of odd numbers. You have 5 odd numbers here. So 5 square is equal to 25, and that's your answer. Similarly, you have 10 odd numbers starting from 1 to 90. So you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Count the odd numbers and square. So 10 square is 100. I have given some practice sums. Please try them on your own. Let us try another type. Express 49 as a sum of 7 odd integers. Remember, when they ask you to write the sum, you must start from 1. So starting from 1, let us write 7 odd integers. What are the 7 odd integers? They are 1, 3, 5, 7, 9, 11 and 13. When you add them up, you get 49. Similarly, let us try another example. 121 as a sum of 11 odd integers. So starting from 1 again, write down 11 odd integers. It will definitely sum up to 121. I have noted some practice sums. Do that in your notebook. Coming to the next special property of square numbers, or let us say to find the non-perfect squares between two consecutive square numbers. Now what do you mean by consecutive square numbers? 4 and 9 are known as consecutive square numbers. When you look into the squares table, you must have noticed that 4, 9, 16, 25 is a series of square numbers coming in order. So 4 and 9 are consecutive numbers, 9 and 16 are consecutive numbers, 16 and 25 are consecutive numbers, and so on. What are the numbers between them? Between 4 and 9? It is 5, 6, 7 and 8. So how many numbers are there? There are 4 numbers which are not perfect squares between the perfect numbers 4 and 9. Let us consider another example. What are the numbers between 9 and 16? You have 10, 11, 12, 13, 14, 15. Count them. There are 6 numbers. So that is, there are 6 non-perfect squares between 9 and 16. Now here again we observe a pattern that the number of square numbers between two consecutive squares is twice the number which forms the smaller square. Or in other words, there are 2n non-perfect square numbers between n square and n plus 1 the whole square, where n is a natural number. Does it sound confusing? It's really simple. Let us solve these sums to know how simple this is. How many numbers lie in between the squares of the following numbers? So the question is, how many non-perfect squares lie between 12 square and 13 square? As per the rule, it is 2 times or twice the smaller number. That is 2 into 12. What is 2 into 12? 24. So there are 24 non-perfect squares between 12 square and 13 square. Isn't it simple? Let us try for 25 and 26. That is, how many non-perfect squares are there between 25 square and 26 square? The answer is double the first number or the smaller number. That is 2 into 25, that is 50. So there are 50 non-perfect squares between 25 square and 26 square. Isn't it simple? Just multiply the first number by 2. It is as simple as that. Try the practice sums as given below. Now, other interesting facts of square numbers. That is, squares of odd numbers. A square of any odd number can be expressed as a sum of two positive consecutive integers. Let us take for example 81. 81 is a square number. What is half of 81? It is around 40 and a half. So, if you put it as an integer, it is 40 and 41. 40 and 41 are consecutive integers. So, any square number can be split in this form. Any odd square number. Odd number. Okay. Now, let us take another example. 225. What is half of 225? It is around 112. So 112 plus 130 gives you 225. That is, two consecutive integers give you an odd square number. Interesting, isn't it? Another property or a pattern which we are going to see now is the product of two consecutive even or odd natural numbers. Let us multiply two odd natural numbers, that is 9 and 11. 9 and 11 is 99. There is an easier method of finding the answer. Find a number lying between 9 and 11. It is 10. Square 10. Find the square of 10. It is 10 square, that is 100. And if you subtract with 1, you get the answer, that is 99. I repeat, the more examples you do, you get to understand these properties better. Let us try another number, a bigger number, for your understanding. What is the product of, that is 249 into 251? It is a very lengthy sum, but we can do using square numbers. And how is that? The number lying between 249 and 251 is 250. Square 250. 25 square is 625 from the squares table, and 0 square is 2 zeros. So if you learn the tables, this becomes very easy. So 250 square is 62500, and you subtract 1, you get 62,499, which is the product of 249 and 251. You can cross check using the regular multiplication. Try these practice sums, 79 into 81 and 119 into 121, to get a better idea of these properties. Now let us recall the summary or the important rules we learned in this particular session. A square number or a perfect square is a number that can be expressed as a product of a number with itself. The numbers which end with 2, 3, 7, 8, an odd number of zeros, are never perfect squares. Even numbers have even squares, odd numbers have odd squares. The sum of the first n odd natural numbers is n square, where n is the number of odd numbers. There are 2n non-perfect square numbers between n square and n plus 1 the whole square, where n is any natural number. The next rule, a square of any odd number can be expressed as a sum of two positive consecutive integers. And the last one, the product of two consecutive even or odd natural numbers is 1 less than the square of the number between them. Now, as practice, do it regularly. You will get very familiar with the rules mentioned here. I hope the session has been clear. I hope you can do the practice sums well. All the very best. Hope you enjoyed the session. Enjoy playing the game of numbers.